Hello, everybody. This is the hands-on with the TigerGraph Graph Data Science Library and Python. I'm Parker Erickson. I'm a machine learning and data science intern at TigerGraph. A little bit about me. Like I said, I'm currently a data science machine learning intern at TigerGraph, also working on my master's in computer science at the University of Minnesota, creator of PyTigerGraph, which I'm sure many of you are familiar with. If not, that's sort of what this session is about too. Basically a Python package to interface with TigerGraph. Formerly interned at Optum, working on machine learning solutions with TigerGraph and patent pending inventor for fraud detection using graph neural networks, as well as some other ML algorithms with knowledge graphs. Here are two links that you're going to need today. The first one is to TigerGraph Cloud. The second one is to our Google Colab notebook. The links are in the description of this session, as well as we'll make sure that they are in the chat as well. Without further ado, we'll go ahead and set up our TigerGraph Cloud instance, and then we'll dive into our Python notebook. So I'm going to go ahead and go to tgcloud.io. And this should bring you to a screen, log in and register. I already have an account, so it's going to log me in already. We'll just sit here for a second. Here you can see the dashboard. You get some free credits, as well as sort of your breakdown of recent activity. But what we're going to do is go into this My Solutions tab over here. Going to go ahead and say create a solution. The TigerGraph version is 3.1.5. And today we are going to be taking a look at a healthcare referral network. So in the starter kit, we're going to scroll down to healthcare referral networks. Right here, there's some other cool starter kits that you can play around with, like a COVID-19 starter kit, a enterprise knowledge graph Crunchbase kit, as well as recommendation engine, supply chain, fraud detection, a whole bunch of different options. But for today, we are going to do this healthcare referral networks starter kit. So we're going to scroll down to the bottom, hit next. The free version we're going to use, this tg.free instance on AWS. Basically leave all these settings the same. You can choose a region that might be closer to you, but for me, Northern California works. Going to go ahead and hit next again. You can name your solution. I'll do like Dev Day Healthcare. The tag should already pop up. Set your initial password. I just go, since this is a starter kit and no real data, I go ahead and use the default password of TigerGraph. You do have to type it in, but remember this password, and this password will be different than the one that you use to create your TG Cloud account with. This is going to be for the actual instance. Subdomain, you get to choose. It does have to be unique. So I'm going to do Parker Dev Day Healthcare.i.tgcloud.com. And if you want to throw in a description, you can do that as well. So here I'll give you a summary. $0 an hour, that's wonderful for us right now with the starter kit of the referral networks. And here's your host name and your, doesn't give you the password, but remember that password and this subdomain. we're going to go ahead and hit submit here. It might pop up with that. You don't need to save it. And then we're going to wait until the server is provisioned, which gives me a little bit of time to talk about some of the graph data science features that we have in our TigerGraph graph data science library. Here we can see basically the main algorithm types that we have currently. One is centrality, so rankings of vertices based on their network and sort of their influence within a graph. PageRank is the big one here. There's some other algorithms like article rank, which we'll also be taking a look at today. We also have classification algorithms. So, you know, this vertex belongs to this group, and learning that classification. We're also going to take a look at a classification algorithm today, Knearest Neighbors. We also have community, so finding vertices within the graph that are very closely related to one another and densely connected. We're also looking into those with Louvain community detection today. Then we have some new features such as our graph embeddings, which take a vertex and come up with a small dimension vector representation of that vertex based upon the community that that vertex is in. Not necessarily community as in Louvain community, but the neighbors and you know, multiple hops away of that vertex, their topological information is captured in those embeddings currently. Like I said, you can convert those in, or those are a fixed sized vector. So you could have like a 64-dimensional vector that represents a vertex using floating point numbers. We also have path finding algorithms. So, you know, finding paths from one vertex to another in a graph, as well as, you know, BFS, DFS, A star, things like those. We have similarity. We have both in graph, well, all of our solutions are in graph, but topological similarity, like cosine similarity based upon the actual neighbors of a vertex, as well as embedding similarity. So you can actually compare embeddings that have already been generated with one another. We also have topological link prediction. So if two vertices share a large number of neighbors, chances are they might have an edge between them. And then we also have frequent pattern mining. So finding subgraphs that occur frequently within your data. And a priori is a good example of that. Here we have a whole bunch of algorithms listed out, complete with links to the GitHub page where they're hosted. We'll make sure that this slide is available as well for you to peruse. And then speaking of the GitHub, it's in this GSQL graph algorithms repository. You have a README, you have a list of all the different algorithms that we have, and then you can go into the algorithms folder, take a look at, you know, maybe we want to look at centrality algorithms, article rank we're going to be using today. So here's a README on how to get started, as well as the query that we can take a look at. You can also copy and paste these queries. They're designed to be schema free. So any schema that you have, these queries should work on them. And then if you need to make a modification, all of this is open source. So, you know, feel free to do that as well. So sort of a summary on this, all these graph algorithms are written in GSQL, open source and modifiable by you, the developers, all available on that GitHub page that we just saw. This underlies, utilizes TigerGraph's advantages of being massively parallel processing in its nature and faster execution times, as well as distributed across a cluster of compute nodes. And GSQL is designed for executing these types of queries. Now, hopefully, we have our box provisioned here. So what we're going to do is go into this, click on this 3 boxes lined up and the 4th tilted button here that highlights applications. And then we're going to go into Graph Studio. And so this should load up. You might have to put in your password on this screen here. I did TigerGraph. So whatever you chose when you provisioned your instance, you should put in here. It'll take you to this screen. And then we're going to take a look at our graph. So we're going to go click on this total view button and then go down to this My Graph button. We're then going to take a look at the schema. And so here we see a prescriber or a provider can have a subspecialty associated with them, which is then further associated with a specialty. Claims are submitted by this prescriber, and these claims are associated with patients. These prescribers, though, can also refer to other providers. So let's say a general practice physician says that you need to see, a surgeon of some sort. We're going to see a referral edge be created here in between that general practice physician and that surgeon. If you move these things around a little bit, you might see this pop up. You can certainly hit leave and you'll be just fine as long as you didn't delete anything. It'll be all good. So here we can see a map data to graph. We already provide all of these CSVs to load the data in. So we can just go to this load data tab here and then click this play button once it starts. And it will say loading, the CSVs to different edges or vertices, and we're going to go ahead and hit continue. And it's going to take a little bit, but we're going to load these here. We can see the trend of loading, and we should see it be complete here pretty soon. And this one's almost done, but everything else is finished. And it looks like our vertices have leveled off at about 11,000 vertices, and our edges will level off around 40,000 edges. We can then go into the Explore graph and take a look around. Maybe we want to look at prescribers or providers. We can take a look here. Here's a whole bunch of claims associated with this provider. Ophthalmology, metabolic system. We can see that their subspecialty is cardiology. We can see other cardiologists that have that subspecialty, and then that specialty of cardiology. There, it turns out that there's other subspecialties below that cardiology specialty. We can also click on some of these claims and see, what patient they're prescribed to or associated with, and see all these other patients' claims. Musculoskeletal system claims here. You also notice that on the provider vertices, when you hover over them, it shows attributes, one of which is a community ID as well as a page rank score. Now, all of these are currently set to 0, but that should give you an idea of where we're going. We're eventually going to store community IDs as well as page rank scores on each vertex, on each provider's vertex. So taking a look at the Explorer graph, we can play around farther in here, or else we're going to dive into the Jupyter notebook here. Like I said, this link is in the description of this session, as well as in the chat. I'm sure that I'll probably post it right about now as well in there, so you can have this as a reference. So, the title of the session, hands-on with the TigerGraph Graph Data Science Library in Python. A little bit more info about the data science library. There's a link here to the GitHub page that we already took a look at, as well as the documentation site of these algorithms. So we can go ahead and look at, maybe we want to look at article rank. We can take a look at sort of how it's derived and the parameters that we should pass in. And then, an example of what that query in the GSQL shell should look like, as well as a result of what we're going to get. And this is true for basically all algorithms, actually all algorithms, is that we have a description and input parameters and the result types and things like that. You can take a look at these and peruse and find algorithms that you might think that might be useful for you in the future on your own projects, with your own projects. So without further ado, we're going to dive into the Python portion. First, we're going to install the 2 Python packages we're going to use today, PyTigerGraph and Pandas. So we're going to just go ahead and click Run here. It's going to go through and download. And then we will be all set. So then we're going to verify that we can connect to our instance. So here we have credentials that you need to change based upon your configuration. So here my host name is parker-dev-day-hc.i.tgcloud.io. So we're going to copy that with the HTTPS, so we know that it's a secure connection, and we're going to fill that in as the host. Username and password, like I said, I'm using the defaults of TigerGraph and TigerGraph. Password you should change based upon what you selected when you configured your instance. We're going to go ahead and click that to run. So it sets up a connection, and then we also need to grab a API token for the REST endpoint. So we also are going to get a token based off a secret that we create and store that in our connection attribute, in our connection class. There's a ton more options here that you can specify based on your specific configuration of TigerGraph. If you need to change the ports on the part mappings or the graph name or things like that, you can do that when you instantiate that this connection object. and then you'll be good to go. One link that I do not have in here that I will add is the TigerGraph documentation and GitHub page. So it's the PyTigerGraph organization / PyTigerGraph for the repo. And here you can, make some PRs if you want to contribute to that, as well as take a look at any of the code underneath the hood if you want to. But then the documentation shows how to get started with installing via pip and then instantiating your connection, as well as all the different functions that we have, including getting specific vertices or counts of vertices or upserting them, running queries, both installed and interpreted, edges. You can also get data frames directly from the graph, as well as upserting your data through data frames, as well as using GSQL. So tons of information here, and I'll make sure that that is added into the chat or into this notebook. So here we got the API token, and now we're just going to verify that we can actually connect to our box. So here we just run an echo, and we get back the hello GSQL that we expect. We also run a GSQL ls command, and that gives us our vertices and our edges, and that the graph is called my graph, and all the loading jobs associated with that, as well as community or queries that are created already but not installed on the box. Speaking of queries that are not quite yet installed, we do need to run a install and run query that creates the referral edges. So if we go back to the Graph Studio page and into load data, we can see that we actually don't have any referral edges currently. So what we're going to do is that there's two queries already created on that instance, and we're going to install them and run it. And while that is happening, we're going to go back into Graph Studio and take a look at those queries. So this create referral edge query, basically given a provider, it looks at the claims that that provider submitted, and then if claims are within claims of the same patient are within 30 days of each other, we assume that the provider that submitted the initial claim provided a referral to the second provider that submitted the second claim. So that's basically what this query is doing. And then we have a main query that applies this to all prescribers in the graph. Going back over to the Colab notebook, we can see that we're still installing these queries, but we'll get that going here pretty soon. This is taking a little bit longer than it usually does. All right, that one looks like it's installed. So now we're working on the main query here. we go into the load data. We haven't run that query yet, but we should see pretty soon here the referral edges pop up as it executes. And there we go. We get some referral edges added. It prints out a result as well, but we were just interested in getting those edges loaded into the graph. So what we're going to do from here is going to perform Louvain modularity community detection. So this algorithm creates communities within the graph by maximizing a metric called modularity. And the higher the modularity, the vertices within that community are more densely connected than that of randomly connected vertices within a graph. So once again, we can take a look at the doc page, or else we, take a look at the doc page just so that you can see there's some papers cited here of some different applications and improvements to the original algorithm. We can take a look at results and the input parameters, as well as the time complexity. So here you can see that it's, V squared. And so that's not terrible, but it's not great either. And then we can then, what I did was took the Louvain algorithm found in the GitHub and just hit this raw button, and that gets you the raw text where you can copy and paste it into the Python notebook. And so you see all the GSQL here defined as a string, and then we're gonna take this and use the GSQL function in our TigerGraph connection to install this query right here. Once that's completed, we're then going to go ahead and take a look at the parameter, or define the parameters that we want to use, and then run the algorithm with those parameters. So we're going to use prescribers or providers, depending upon the way you want to phrase them, and look at the referral edges as the edge type. We're going to use the weight edge, or we're going to use number of patients as a weight on the edge in between referral, between prescribers as weights on the referral edge. And then we're going to use some, we're going to use 10 iterations for each iteration here, as well as print the result as JSON, and then also store the result as an attribute of community ID. So going back to the schema, we want to store our community information for the vertices on this attribute of each vertex. We're going to go ahead and hit run on that. It comes back. Here, we can go ahead and take a look at the cluster, number of members in each cluster. So, community 681-57441 has 11 members in it. 72351744 is the largest community with 29, and 3 communities have 8 providers in it. So we can also take a look at getting the providers given a community. So we can print these out with this function. All of this information is stored in this result dictionary JSON object that is returned from this run install query call. So, if we're interested in the providers in the largest community, we take that community ID and then we can print those out as this function parses the JSON to get that information for you. So we're going to then move on to PageRank, which originally was developed by Google, and it scored more influential web pages higher than less influential ones. And this influentiality score is based off of the importance of pages that linked to that page. And so we can find more influential or central vertices to the graph based on how the vertices that connect to it are, how central or influential they are. So it's sort of a recursively defined concept here. Like I said, here we have the documentation link, and then I did the same exact thing for this one as I did with the Louvain algorithm, is I went into the GitHub and copy and pasted this, and then defined that as a string, and then gonna go ahead and install that PageRank query. We are working on better integration with Python, TigerGraph, and our GSQL library of algorithms. So eventually you won't have to go through this process of copying and pasting and then installing. You could also pre-install these on Graph Studio. I personally find that it is better, or it's nicer for me to see and work in one Python notebook than jumping back and forth all the time. But it is sort of lengthy, so we are working on better integration with those. We're going to then go ahead and do the definition of our parameters. And once again, we're storing our PageRank score as an attribute in the schema on the vertex, and using prescribers and their referral edges to determine these PageRank scores. So that runs in a second and gives us back our PageRank results in a JSON once again, which we can parse, and we can find the most influential providers in a community. So by grabbing the providers within a community, and then we can sort through the most influential, to find the most influential one given a list of providers in a community. So then we're going to move on to article rank, which is very similar to PageRank, but it does lower the importance of low-degree vertices. So low-degree vertices are vertices that have few edges coming in or heading out of them. And so that sort of alters the scoring metric based on some of the different attributes of how this compares to PageRank, but we're going to dive into that a little bit more in the near future. So once again, I copy and pasted the query from the GitHub and then installed it once again, and then we can run it and get all of the article rank results into a JSON as well. So before diving into some analysis, we're going to run one more algorithm called Knearest Neighbors. This is not necessarily the greatest use case for Knearest Neighbors, but I thought it was an interesting demo to show. And what we're going to do is basically predict if a prescriber is in which community a prescriber is in based upon its distance from or based upon its most similar providers. So what we're going to do is take a look at this. We have a subquery and a main query in this algorithm. So the subquery goes ahead and finds the most similar vertices within a graph to a given vertex, and then we take that result, and based upon the class of those 5 most similar vertices, that's the classification that the vertex that we're wondering about and want to classify takes. So we also then perform cross-validation in this main query to find the best K value, which is the number of neighbors that we take into account. So, 3 nearest neighbors is sort of on the low end, but we're going to try Ks in between 1 and 7. So a K of 1 would mean find me the most similar vertex in the graph compared to this vertex, and whatever classification that most similar vertex has is the classification of the vertex that we're interested in. Versus a K of 5 would be sort of a majority voting situation of if 3 out of the 5 most similar vertices have a classification, then the next the vertex that we're interested in will take that majority classification. So here, once again, we use prescriber and referrals and reverse referrals, and the number of patients as a weight. And our label is the community ID, because that's what we want to be predicting. And then we set our minimum value of K to 1 and our maximum K to 7. And we find out the best K value is 5. So in order to better classify communities based off of nearest neighbors within the graph, it's suggesting that we use 5 nearest neighbors. Now, diving into some of the analysis that we can do with these algorithms, we're going to look into subspecialty and get some subspecialty information by writing this query here. Here, what we want to do is we want to create a feature, basically representation for each prescriber in the graph. So we define a tuple, and that gets us our subspecialty, our community ID, and our PageRank score. And then we have a mapicube of prescribers and features of this tuple. So we start with all subspecialties, we get prescribers, and then for each prescriber, we create a tuple consisting of its subspecialty, the community ID it has, and the PageRank score. So we install this, and then we can go ahead and run that and do some data frame manipulation here. And we end up with a provider features data frame that has the provider ID, the subspecialty that it's associated there, the provider is associated with, the community ID, the page rank, and the article rank. And so first, we're going to compare page rank and article rank with one another. So we're going to see first what subspecialties are the most influential based off of these page rank and article rank scores. And we can sort of see here, they're pretty similar. It looks like shoulder surgery is the highest in both of these, followed by some other surgery. Knee surgery is number 3 with page rank and number 2 with article rank. Generally, these are pretty similar, but we can quantify this in just a second. here I thought it would be interesting to analyze the scores of the page rank and the article rank compared to the frequency of that subspecialty. And the thinking behind that would be if a subspecialty is being, there's less of that subspecialty within the graph, then possibly those subspecialties, those specific providers that had that subspecialty would be referred to more. And so that sort of seems to come through here with knee surgery being the least occurring subspecialty of providers in our data, and it having some of the higher page rank and article rank scores. But it's not always the case. And so what we're going to do then is look at the actual correlation between frequency, page rank, and article rank. And so here we do a little bit of more data frame manipulation, where you see the frequency of which the subspecialties occur. So there's 12, here with a page rank of this and an article rank of this. There's 8 general practice providers in our graph. And here are their page rank and article rank scores all the way through knee surgery, where there's only 2 providers, and their article rank and page rank scores are here. We then can run correlation on the frequency, the page rank, and article rank in pandas, and we see that article rank and page rank are very highly correlated, with about 0.8 with each other, while frequency is actually not highly correlated or almost slightly negatively correlated with the page rank and article rank score. And we would expect it to be negatively correlated in the fact that my initial hypothesis was that specialties that have fewer providers, those providers would be referred to more, and therefore have higher article rank and page rank scores, and therefore they would be inversely related with one another in terms of frequency and score. And so article rank sort of captures that, but both of these values are so close to 0 that it does not appear to have much influence on that frequency does not have much influence on the page rank or article rank scores. We then can look at the page rank and article rank scores within communities, and see that some of these communities have higher average page rank scores compared to others. And then diving into subspecialty occurrences within these communities, and we can scroll through here. So article or page rank suggests that community 723511745 has the most central vertices on average. And so we can scroll through here and find that community, and we see that it's generally all specialty physicians. Compared to if we look at some of the lower influence ones, we can see that they might have some more family practice or general practice physicians in them, compared to some of these other ones that are more specialty focused. But generally, these specialties are relatively evenly distributed throughout each community. Definitely more analysis could go into this, and we'll sort of leave that as the exercise to the reader. But With that, I would like to thank you for watching. Any questions, please put them in the chat, or else there's also links on here to our community forum and community Discord, each of which somebody will be able to get back to you and hopefully answer some of your questions. And I would like to thank you for watching. I'll be in the chat to answer any questions, and hope you have a good rest of your day.